Hi, in this video we are going to continue on Unit 5 Atomic Structures. Now we are going to move on to Part 5 here, Relative Isotopic Mass and Relative Atomic Mass. Now before I start talking about this one, I just want to do a quick revision on isotopes. So we say that for a same element, there could be different atoms, and these atoms, they have the same number of protons because being the same element, they must have the same atomic number. And when they have the same atomic number, they should have the same number of protons. So for these atoms of the same elements, they have the same number of protons, but they could have different number of neutrons. So these are what we call the isotopes. Now, when they have different number of neutrons, they will have different mass number as well. So in other words, they have different mass, but they are belonging to the same element, right? And last time we looked at some examples, and these are very typical common examples, and hopefully you are able to memorize these. Now, for chlorine here, I want to talk a little bit more because I will going to use chlorine as an example to illustrate the concept down here. Now, for chlorine, you see it has two isotopes. We can call this one chlorine 35 or chlorine 37, all right? So it has only two isotopes. Now, let's just say, now I'm going to make use of the empty space on next page, and I'm going to jot down something. Now, let's just say I have a sample, okay? I have a sample, okay? And this sample is a chlorine sample, and inside we have 100 chlorine atoms. Right? I have 100 chlorine atoms. My question is, what is the mass of this sample? Right? This is my question here. What is the mass of this sample? Right? Now, you will know that, okay, chlorine atom, we have two different isotopes, right? One is called chlorine 35, another one is chlorine 37. One is lighter, one is heavier. So let's just say we have 100 chlorine 35. So like all of these chlorine atoms are chlorine 35, then, so if this is the case, okay, then the mass would be very simple, right? 100 multiplied by 35, that would equal to 3,500. Okay, that is easy. Now, what if all of these chlorine atoms are chlorine 37? Then the total mass would definitely be 100 minus multiplied by 37, which is equal to 3,700. Okay? Now, but in reality, you will expect to have a mixture of the two isotopes. So that means the total mass of the sample should be in between 3,500 and 3,700, right? So what should be the mass then? Now, some of you may suggest, okay, how about we do like 50-50, okay? Maybe like there are half of them, right? So we are taking the average. So if there are 50, like chlorine 35 and 50 chlorine 37, okay, then we would expect to have like 50 multiplied by 35 plus 50 multiplied by 37, right? And that would be 3,600, okay? Or if you are smart, you can think about it as 35 plus 37 divided by 2 multiplied by 100. So basically taking the average, okay? Now, so can we say that, okay, it is like 3,600, like taking the average. Now, it kind of makes sense, right? Using an average value. But when it comes to reality, we want to know what are the ratio of the two isotopes exist in the nature. For different elements, they have different types of isotopes. Some will have like 2 isotopes like chlorine, some of them will have like 3 isotopes, 4 isotopes, something like that. And most importantly, these isotopes, they exist in different ratio, right? In this case, actually, for chlorine, in reality, we actually say that for chlorine 35, there are 75% altogether existing in the nature. Now, we just found that it is the case in the nature. There's no explanation. It just appears. It just happens to be like 75% of it is chlorine 35. And for chlorine 37, it has to be 25% because, like I said, we only have 2 types of isotopes for chlorine, right? So if that is the case, and if we are finding out the average, then we cannot simply have 35 plus 37 divided by 2. So we will have to have like 35, okay, multiplied by 75% plus 37 multiplied by 25%. All right? So because we are talking about 100 isotopes, so all together here, multiply by 100, okay? So then you will be able to tell, or if you cannot calculate it in your mind, you can use a calculator. So 35 multiplied by 0.75 plus 37 multiplied by 0.25. So this is the value that you get inside this middle bracket. So basically you got like 35.5 multiplied by 100. So the total mass of this 100 chlorine atom would be 3,550. All right. So here we are talking about the mass of 100 chlorine atoms, okay, which is 3,550, all right? So at the end, if I want to find out the average mass of one chlorine atom, then it has to be 3,550 divided by 100, which is 35.5, right? You realize that it doesn't make sense if each atom is 35.5 because these are all the relative mass, right? And each proton, each neutron contribute to the mass. And you remember that one proton contributing one the relative mass, one neutron contributing one relative mass. So if you have a decimal number, that means you have like half a proton, half a neutron. It's impossible because, like we said, that these subatomic particles should be the smallest, right? So you don't expect to have a chlorine atom having a relative mass of 35.5. This is what we call the average mass. Plus, is it simply an average mass? If it is an average mass, then it will be something like this, where we assume that it is like 50% of chlorine 35, 50% chlorine 37. We simply add them together divided by 2. Then that would be an average, like 36, right? In other words, like the average of 35 and 37 would be 36. But we are not just doing an average value. Here, we also consider the percentage, right? We also consider the percentage. So instead of saying that it is an average mass, we will add one more word, which is weighted. Weighted average. It's a weighted average, okay? So weighted basically means we look into the percentage, we look into the abundance in the natural sample. Okay? Now, here I will fit in two more terms. Now, here, this value is the weighted average mass of an element, and we have a specific term for it. We call this one relative atomic mass. Okay, relative atomic mass, because this one representing the weighted average mass of all the atom. Okay, if you have 100 of this chlorine atom, if I ask you the mass of it, like my initial question here, then you can simply use this one, 35.5, and multiply like 100, then you will have the mass of that sample. Okay? Now, you realize that this relative atomic mass is derived from these two masses of isotope. So for these two, like 35, 37, now these two, we call this one relative isotopic mass. Okay, relative isotopic mass. Each of these are representing the relative mass of an isotope. Okay, and the weighted average isotopic masses would be the relative atomic mass. So here, the weighted average mass of one chlorine atom, the weighted average mass is derived from each isotopic masses. Okay, so this is the idea. So make sure you know these two terms. As a quick conclusion, we say that elements exist in various isotopes. Different isotopes are different mass, and they also exist in different percentage. So if you're asked to find out the mass of a particular sample, we want to look into each isotope and their relative abundance. So to calculate the relative atomic mass, or to calculate the mass of that particular sample, we need to first find out all the relative isotopic masses, and we want to multiply their corresponding percentage, or we call it relative abundance. And the weighted average of all the isotopic masses would be representing the relative atomic mass, which would tell us how heavy your sample is. Okay, so that's the idea. Now, once you understand all of these, then now we will go back to the previous page and we highlight some key points. Now here, so first of all, you see, I need to apologize because of the printing problem. All of this supposed to be a superscript. The 12 here is supposed to be a superscript, but I don't know why it becomes a subscript. So for all of these, make sure you rewrite it into a superscript. Because you know that for the bottom left corner, that one is the atomic number. But here we are showing the mass number, so you must put it on the top left-hand corner. Now here, relative isotopic mass is simply the mass of an isotope. But here we have one more part that we haven't talked about, which is compared to the scale of carbon 12 equals to 12 here. Now let's just highlight it, and then after all of this discussion, I will come back. Okay? Let's just look at the two definitions first. Now down here, relative atomic mass. So this one, please, very important. It is the weighted average isotopic mass of an element. Okay? So again, it is compared to the scale of carbon 12 equals to 12. So this one, very important. Weighted average isotopic mass. Okay? And this is like the equation. Now, I'm not sure if you understand this. This symbol means summation. Basically means like if you have two isotopes, then you will have like isotope 1 multiply is percentage plus isotope 2 multiply is percentage, so on and so forth. If you have like three of them, then you have isotope A multiply the percentage plus isotope B multiply its percentage plus isotope C multiply its percentage, something like that. And then divided by 100%, okay? Now, this is like the general equation. If you use decimal number, you don't have to divide it by 100. You get it? Now here, so down here, this is what I mentioned. So isotope of an element exists in different proportion. Okay, different proportion in nature. And this is what we call the relative abundance. So relative abundance means the percentage of each isotope exists in the nature. And that has to be a constant. Okay? For example, chlorine-35, chlorine-37, each of them are like 75 and 25% respectively. Then you can plug these into the equation, you get this one, and then you calculate the relative atomic mass. Okay? And lastly, no matter its relative isotopic mass and relative atomic mass, because you see the word relative, so they are all in relative sense, and therefore both of them carry no units. Okay? Now the last thing is here. So like I said, it's relative, right? And before I said that we define the mass of a proton being 1. Do you remember? I defined the mass of proton being 1, and then we compare the mass of proton to neutron and electron, and then we establish the relative mass of proton, neutron, electrons, right? In fact, the actual story is based on this carbon-12 isotope. But you know, because we haven't talked about isotope before, I can't take this actual reference. But now let's just make everything clear. No matter, whenever you come across relative, it has to be relative to this particular scale, which is carbon-12 isotope equals to 12. Now the idea goes like this. The scientists, they have chosen this carbon-12 isotope as the reference point, and they define the relative mass of carbon-12 isotope being 12, just like that. And then they try to compare for different atom, different isotope, different elements. They try to compare the mass with this carbon-12 isotope and see how much heavier, how much lighter, and then they are able to establish all of these relative isotopic masses. Okay, so it's just like a balance. You can think about it as a balance, right? So it's like not a balance. It's like a scale, right? You have like a scale like this, and just now here we are trying to say that for magnesium-24, you can imagine having like 2 carbon-12 here on one side, and then we have a magnesium-24 on the other side. And if we kind of balanced it, that means the magnesium isotope, magnesium-24 isotope, is twice as heavy as a carbon-12 isotope, and therefore magnesium-24 isotope is having a relative isotopic mass of 24, just like that. Okay, now one more thing before we move on to the actual calculation. If you look at the periodic table, now this is the periodic table on the last page of your note. You realize that there are a number below each element, and those numbers are mostly in decimal numbers. These are what we call the relative atomic mass. Okay, you see the word relative atomic mass. So basically, you can find the relative atomic mass from the periodic table. These are all the weighted average isotopic mass of each element. Okay? Now, you see hydrogen is 1. But sir, you may say, isn't you said that the isotope of hydrogen is like 3 of them, right? So the relative atomic mass should be in between 1 and 3. So why it is like 1 over here? Now, actually, it is true that it is a weighted average isotopic mass of all 3 isotopes of hydrogen. But it could be the case where actually like 99.999% of the hydrogen isotopes are being hydrogen 1, right? And in reality, it is also the case. So that's why even you calculate the weighted average of 3 of them, you end up with a number very close to 1. Like the majority of the hydrogen isotope is hydrogen 1. So that's why you get like 1 here, right? For some of the isotope, if my memory serves me right, like argon, argon being faulty because the majority of the isotope is really argon. And I remember like some of these elements are actually having only 1 isotope at all. So the relative atomic mass will be the same as relative isotopic mass. Okay? So that's the idea. Now, let's just look at an example, a worked example. Maybe I will do one as a demonstration. Now, you see at the back here, we have 7 questions, right? And I would like to do the first one as a demonstration, and then I will looking back to the worked example, because the worked example is a little bit advanced. So I'm going to like go through 2 examples for you, and then you will pause the video and do practice. So here, the first one, let me do it. Now, it says that magnesium has 3 isotopes exist in the nature, and the relative isotopic masses and the percentage abundance are all shown down here. Calculate the relative atomic mass. So, you know, the relative atomic mass is the weighted average of all 3 isotopes. So here, you can have this one, right? So it's 24, 78.7%. So you can have like 24 multiplied by 78.7. And then you can have the magnesium 25. Now remember, it's plus, okay? 25 multiplied by 10.1. And lastly, you can have like magnesium 26. So 26 multiplied by 11.2. And overall divided by 100. Okay? Now you can do this. You can divide it by 100, or you can use a decimal number here, like 0.787, 0.101, 0.112. Okay? Just suit yourself. And then you just have to tap your calculator. So you like 24 multiplied by 78.7 plus 25 times 10.1 plus 26 times 11.2 divided by 100. You should have 24.3, usually with 3 significant figures. Now, remember, there are no units, and actually, you can also double check with all these numbers. Like I said, this is a weighted average value, so this number should be in between 24 and 26. If you got something like 23 point something, then you must wrong. Another thing you can double check is here at the back, like magnesium 24.3. So if this one is very similar to your answer, then mostly you are getting it correctly. Okay. Now this is a very simple example. Now let's look at another way, another type of question, which is the worked example from the previous page. So here, this time, they tell you that, okay, rubidium contains 2 stable isotopes. So calling rubidium 85 and rubidium 87. Now it tells you that the relative atomic mass is 85.5. So calculate the percentage of each isotope. So this time, instead of asking you the relative atomic mass, they actually give it to you, but they ask you the percentage of the 2 isotopes. Okay? So it's a little bit mathematic. Basically, you need to assume or let like Y% to be the relative abundance of one of the isotopes. It could be rubidium 85, it could be rubidium 87, it doesn't matter. So let's just say rubidium 85 is Y%, then rubidium 87 must be 100 minus Y%, because these 2 are the only 2 isotopes. When these 2% are added together, it has to be 100. So you think about it, 100 minus y plus y definitely equals to 100%. So this is how it works. Then once you get this one, then you can simply plug into the equation. So you remember having the mass, the isotopic mass multiplied by the percentage plus the isotopic mass multiplied its percentage over 100 equals to 85.5. Then you can simply solve this simple equation. Then you will get y equals to 75. Okay, so if y equals to 75, then 100 minus y will be 25. So it turns out that it is rubidium 85 being 75% and rubidium 87 being 25%. So this is how it works. Now these are the two very typical type of questions, and at this moment I would like you to spend some time working on these calculations. So we have 1, 2, 3, 4, 5, 6 questions left. So pause the video right now and try to work on this question, and then we will check the answers. Okay, let's check the answers. For the second question, so for oxygen, it has 3 isotopes, and they give you the percentage as well and calculate the relative atomic mass. So it is actually the same as this one. So relative atomic mass equals to 16 multiplied by 99.76 plus 17 multiplied by 0.039 plus 18 multiplied by 0.201 divided by 100. So you tap your calculator. So you got 16.00. Okay? So now after you do this calculation, give you a tips. You can also double check to see if your answer is sensible or not. Because you think about it, with 3 isotopes being almost 100% oxygen 16, then the relative atomic mass should obviously be very, very close to oxygen 16, right? It's like almost all of them are oxygen 16. So this number, if you get a relative atomic mass that is very close to a particular isotope, that actually tells you that that isotope is having a very, very high relative abundance when compared to the others. Okay? Now, let's look at question 3. Again, it's a very similar question, so let's do it quickly. 6 times 77.4 and then 7 multiplied by 92.6 divided by 100. Now again, you can tell, like more than 90% of it is lithium 7. Then I would expect the relative atomic mass should be very close to 7, maybe 6.9, something like that. So let's have a look. 6 times 7.4 plus 7 times 92.6 divided by 100. Yeah, so you see, it's very close to 7, 6.9. Okay? Okay? All right, so the fourth one here. Again, a very similar question. So you got 69.8. Okay? Now, question 5 is a little bit different because this time they give you a graph. So this graph basically tells you the relative abundance of the 3 isotopes. So you have to get all the percentage from the graph, but it's not too difficult, I guess. So here for 206, I think this is 22. And here I think it is 23. It's a little bit more. And this one, even you can't read it easily, you can tell it has to be 55 because all of these added together must be equal to 100. Okay? Then you can simply do the similar calculation. 206 times 22 plus 207 times 23 plus 208 times 55. Okay? Divided by 100. So you got 207.3. Okay? All right. Question 6. So actually, if you realize that question 6 is the same as the worked example. So same as the worked example. So I don't repeat myself. You can refer to the previous page. So let's look at question 7. So question 7 here. Now this is the type of question that is very similar to what you would expect to have in your exam. Because in your exam you can't use your calculator. So for these calculations, we will provide you with numbers that are manageable without a calculator. So questions like this would be similar to those that we will have in the exam. Now here, two main isotopes, neon 20 and neon 22. Relative atomic mass is 20.2. Calculate the relative atomic mass. Calculate the relative abundance. So here, first of all, we need to let Y percent be the abundance of one of them. Let's just do neon 20. Then 100 minus Y percent will be the abundance of neon 22. Okay? Then we can just plug it into the equation. We have like 20 multiplied by Y plus 22 multiplied by 100 minus Y divided by 100 equals to 20.2. Now this time I don't use a calculator. Multiply both sides by 100, so you get 20Y plus 2,200 minus 22Y equals to 2020. Okay? Then 20 minus 22Y, negative 2Y equals to, so 2020 minus 2,200, then you will get negative 180. So Y equals to 90. Okay? So therefore, the abundance of neon 20 is 90%. Abundance of neon 22 is 10%. Okay? Just like that. Okay, so that's it for the relative atomic mass and the calculation. And that's it for the video.